Okay, so let's get started. So can everyone see my screen?
Yeah.
So hi everyone, welcome. My name is Kobe, and today let's dive into reinforcement learning 101, which is learning to act from rewards. So why reinforcement learning matters? So I'm going to bring some quote from the famous two researchers named Richard Sutton and Andre Battle. These two are the pioneers of RL, and they are both Canadians actually. So the idea that we learn by interacting with our environment is probably the first to occur to us when we think about the nature of learning. When an infant plays, waves his arms, or looks about, he has no explicit teacher, but it does have a direct sensory motor connection to its environment. So the core idea is that we want to use reinforcement learning to bring this idea to machines. And so why reinforcement learning? You probably have heard that in 2016, the famous Go player named AlphaGo AI, it defeats the top player named Lee Sedol. And here the game 2 move 37, which is the move that confuses most of the experts. And it actually has a odds of 1 out of 10,000. And turns out that this move is actually the winning move for the AI. And another famous application is ChatGPT trained with human feedback that actually learns how we prefer the conversation to go. And lastly, robots learning to walk is another example. And reinforcement learning actually has some roots in animal psychology. For example, if you want to train your pets, you may use negative reinforcement such as pain and hunger. You may use positive reinforcement such as pleasure and food. And so the idea is we train animals with rewards, and can we train machines the same way? And so the idea here is that we're learning to act through rewards, which is called reinforcement learning. So what problem are we solving? The key line here is that how can we act when we don't know the best action? For example, if we are playing a new board game or if our company is trying a new business strategy. So you have to try, you have to observe, and then you have to improve your strategy. And so decisions are typically not isolated, they happen over time. So for beginners, you just need to know that IL is basically you learn from try and error. You try some action, you observe some rewards, and you observe from errors as well. For engineers, we typically denote this as sequential decision making because we have to make decisions in sequence and not in parallel. And typically the signals are delayed. So let's say I implement a new business strategy, probably you'll observe the change in the next quarter's revenue. And for researchers, we typically denote this as maximizing what we call cumulative reward over time. So typically, we take some action, you will have some reward, and we take an action, you will have some other reward. However, typically, it may be action, reward later, and it will typically be a delay signal. So, what is the core idea of reinforcement learning? The basic idea is that an agent that interacts with an environment to maximize some notion of reward. And here you probably know there's some robot that tries to clean your room. In this example, the agent is your robot. The environment is, say, your living room. Then the actions can be move forward, move backward, and clean the current location. And the reward, you may praise your robot or you may criticize your robot. And the idea is that the interaction will happen repeatedly over time. So to simplify this, we have a robot, we take some action, the environment will give out some feedback, and the robot will use this feedback to potentially improve its actions. And so here we have the typical reinforcement loop. Basically, it's a loop version of the previous slide. We have an agent that takes an action. The environment will output the next state, and it will output a reward for the agent. And the agent will take in these two information and continues to improve its actions. So we observe a state, we take action, we receive the reward, and the key points, there are three layers. First layer, you can think of this as simply a loop of observe, act, learn, and repeat. And if you want to code this in Python, typically we have an environment dot step action. So this is where you take a specific action in the environment. And for researchers, we define this as a trajectory that is defined as state action reward triples. So we have state action reward next state, and we repeat this cycle. And so here, let's look at a running example, which is a card pool. So this is a simple environment in the OpenAI gym. So the state, there are a few of them: the card position, the card velocity, the pull angle, and the pull angular velocity. The goal of this example is to move the card pull to a certain direction, either to left or right, and to keep the pull balance for as long as possible. And for every time step you manage to balance the pull, you get +1 for reward. And if the pull tilts too much, the episode ends. And this environment is available in the Capo V1 in Gymnasium. And this is a continuous state space with discrete actions because the state values, they are actually continuous value, while the actions, there are only two of them, which is just left and right. And here, let's play a video. Basically, so you see, we try to move the card to either to the left or the right. And the idea is to keep the pull as balanced for as long as possible. And so you may think, is it reinforcement learning very easy? The answer is not. So learning from interaction is actually much harder than supervised learning. The first idea is that you don't know what actions are good. And secondarily, rewards often come later, not immediately. In the previous example, it is true that you get +1 reward for every time step you stay upright. However,
Okay, so let's start. The
in
card
many other
system is shown in this figure. It consists of a card that can move linearly, that is, it can move in this direction or in this direction, and we have a rotating pole or a pendulum attached to the card. Here is the page.
Yeah, okay, yeah. So what makes reinforcement learning hard? So the first idea is that you don't know what actions are good. Secondarily, rewards often come later, not immediately. So in the previous example, we see that for a +1, you get reward every time step you stay upright. However, in most of the environments, the reward often comes later. And so the key question is, did this action actually cause the reward? For engineers, the challenges, there are a few of them. The first one is as the same as the first one. The feedback is often sparse and delayed. And the second problem is we need to balance exploration versus exploitation. So do we want to explore a bunch of different actions, or do you want to try, or do you want to take actions that seem good to us? And finally, it's hard to cover all states and actions because typically all of them are continuous. And finally, for researchers, the main two problems are credit assignment problem. So how do we know which action actually causes the reward to happen? And second problem is the data is actually non-IID. So in traditional supervised learning, remember that we have pairs of input and output, and typically we assume the inputs are independent. However, here the inputs are typically not independent because your next state is going to depend on your previous state. So data is not necessarily identically distributed. And so now we explore the first problem, which is exploration versus exploitation. And let us step back a little bit, and we may realize that in our life, it's actually a balance between trying new things and sticking to what works. So, as a researcher or engineer, we may explore different topics early, and then we may choose to focus deeply on one of the favorite topics. And the question is, when should we switch? And so reinforcement learning agents actually face the same dilemma as human. And for engineers, exploration typically just means try new actions for the agent, for example, for your robot. Exploration means just choose the best known action. And trade-off is, can we balance these two? So how do we avoid too much exploration versus too little exploration? And finally, for researchers, there are a bunch of concepts. The first one is epsilon greedy. So the idea is that For 90% of the time, we take the best action. For 10% of the time, we take a random action. And upper confidence bound, basically, we estimate the value of a certain action, but however, with some sort of a standard deviation, and then we do some form of a sampling. And this is known as a fundamental trade-off in decision theory. So the idea is that your cut pool agent must explore before it learns how to balance itself. And now let us move to a formal concept which we define as a Markov decision process. This is usually underlying the hood of your RL agent. So the simple assumption is that the future depends only on the present state, and this is what we call the Markov property. So for example, your state S1 will only depends on state S0. And so the idea is that you don't need to see the full history, and the current state already contains all the necessary information. So the question we would ask is, given what you are now, the past actually doesn't matter. For engineering, if you want to implement this, we typically model this as a transition tuple, where each transition is denoted as the current state, the current action, the reward, and also the next state. And this is what we get typically from env.step action. You will return a tuple of next state and then basically also the reward as well. And for researchers, we have the following formal definition, which we might see this in IR papers. We define an MDP as a collection of states, a collection of action, a collection of transition function. Basically, this decides what next state will we be in given the current state and current action, and also what reward we may get if we take the action in the current state. And finally, a discount factor gamma basically means that $1 today will worth more than $1 tomorrow. And so what is the objective of reinforcement learning? In mathematically, we basically use this function which we could know as GT. So GT basically is an infinite sum. Basically, we collect the reward at each time step, and then we take gamma to the power of k because we discount future rewards. And because future rewards matter less, as we just explained that $1 today is worth more than $1 tomorrow, and this will ensure the sum stays finite instead of infinite. Typically, gamma is set between 0.95 and 0.99 in practice, and this will ensure convergence of infinite horizon regions. And so the key line is that we care about long-term reward instead of just immediate reward. So policy. So how can we act? So given a state, how should the agent act? So here we have a policy, basically tells the agent what action to take in each state. And we denote our policy typically using pi. And pi takes in a state S and it will output an action. And for beginners, it's quite simple. A policy is just a strategy. So given this situation, what should I do? For example, given our company's current situation, what product should we sell to our customer? For engineer, a policy can be two things: a function, or maybe some form of a hard-coded rule, or it could be a neural network that takes in the state and outputs some action. And finally, for researchers, there are two kinds of policy that you may be aware of. The first one is deterministic policy. So given the current state, I simply take the available best action. And stochastic policy typically gives a distribution of actions. So for example, if there are 4 actions, then, and let's say the best action is going upwards, for stochastic policy, we may assign a probability of 0.9 to up, and we may assign 0.05 to the action going left, and then we sample from this distribution. And this policy is typically what we will learn in reinforcement learning. And a good policy is one that can lead to high long-term reward. And now, how can we evaluate a given state? And now we will bring in value function. So we assign a value to a state or a given state action pair. For state value, we denote the function as Vs. So this question asks, how good is this state? Or we may assign action value, which we denote as the quality function that takes in a state and an action. That basically means how good is taking this action in this current state. And QSA typically helps us to choose action. For beginners, we just need to know that how good is this situation? How good is this choice in this situation? And the value typically you just need to know that it equals the expected future reward, basically the GT value that we talked about earlier. And for implementation purposes, you may represent these functions as tables if your states and actions are discrete, or you may represent this function as a neural network for large problems. And for researchers, the view is that these are actually expectations of future trajectories, because if you look at this function, so the R is actually, this is actually an expectation instead of computing the summation, because in the infinite setting, it's actually an expectation. So basically, we denote as expected cumulative reward under a given policy. And now we can talk about the famous Bellman equation, which denotes as Vs, the value of a given state, is actually denoted as the reward of SA plus gamma times Vs prime. And we wish to find out which action result the highest value. So for beginners, the intuition is very simple. Good decisions should be able to lead to good situations later. So your value of your current state should equal to your current reward plus the future value of the state. And for engineers, we break this typically into two parts. The first part is your immediate reward ISA, and the second part is the discounted future value, which we denote as gamma times Vs prime. And for researchers, we define as a recursive definition of your value function. And this is the foundations of many dynamic programs and also the foundation of early IL programs. And this will turn long-term problem into a sequence of short-term decisions. So let's give a preview of what may come next. In the next few weeks, we'll cover a bunch of interesting topics. We'll begin with value-based functions. So how can we learn values? And how can we use this value to choose actions? And these are the bedrocks of many algorithms such as Q-learning and deep Q-learning. And in the next few weeks, we'll also talk about the policy-based methods. Can we directly learn the policy instead of just learn the value network? And this is denoted as the reinforced method. This is the earliest policy-based method. And then following these two, can we actually combine them into one agent? Basically, this is a foundation, what we call the proximal policy objective, the PPO. And in week 5, we'll talk about AI with humans. So typically we have an environment, and then the environment will output some reward. Now, can our human actually assign reward to our AI agent? For example, ChatGPT, can we teach it to follow our preferences? And finally, we end this with world models. This is a very exciting direction because world models will be the foundation for AGIs. And so can we learn a model of the environment and then apply it to our AI methods? And this is the foundation of methods such as Dreamer and Mu0. So early world models are used to play Atari games, basically the arcade games. And so the roadmap here is we learn the value, we learn a policy, we combine them, and then we may use human rewards, and then we apply it to world models. Now, you may ask, what are the applications in the real world? Well, the most famous one is probably self-driving cars. So this is an example of a robo-taxi in my hometown, Wuhan. So in this city, self-driving cars can now navigate complex real-world environments. So here, the state would be road conditions, traffic, and pedestrians. The actions may be accelerate, brake, or turn, and the reward could be depend on safety, efficiency, and the comfort to the customer. So IL is not just Siri, it powers real intelligent systems. And other examples include your robots that try to walk, the game AI such as AlphaGo, and finally LM alignments such as ChatGPT and all sorts of large language models. So how does IL looks in code? For simplicity, we use pseudocode. So for each episode, we given the current state, we take some action, given some policy, and use this action will obtain to the next state and the reward, and we transition to the next state. So at the bedrock, RL is basically a loop of interaction that consists of observe, act, learn, and repeat. All of the RL algorithms will differ how they update the policy value. So this is you see here is the inference time, and the algorithm will learn either the policy or learn the the value of the state or learn both at the same time. And how they learn is what these algorithms differ. And what
Actually, can you can I ask you to pause a second? Can you just like walk through us line by line on this code?
Yeah, sure. So we start with each episode. So assuming this is the inference time. So state equal to in v dot reset. Basically, this will give us the initial state of the environment. While not done means that we are still in the current episode. Policy state, basically, this will give us the action to take next time. So it may be a distribution we may sample, or it may be a deterministic action. After we obtain the action, we will basically step the action in the simulation, and the simulation will return us the next state and the reward, and then we transition to the next state, and so on and so forth. So this is the inference time and not training time.
I have a question.
Yes.
When you say not done, are we doing epochs, like a number of steps that are predetermined, or is it a convergence function whereby we just wait for the function to converge?
Typically, for each episode, there is some termination state. For example, if your pole turns too large angle, then the episode will terminate. Or you could set it to be, let's say, 30,000, 3,000 steps.
Got it. Thank you.
No worries. Any other questions? And so why is RL still hard? There are actually a lot of active research problems. For example, the first one is sample efficiency. So in supervised learning, for example, if you want to learn to classify images, it's actually very easy to collect millions of samples. However, in RL, it's actually very expensive to collect data. For example, if you want to collect data for a self-driving car, you may find it very costly to, for example, put your simulation to the road, or even to run the simulation on your computer. It's actually very costly. Secondly, stability. So this is more of the training step. So your training may oscillate widely because of the non-IID problem of your data. And thirdly, generalization. This is very important because when you train your agent, for example, your self-driving car, your car will only see a limited number of states, and it's impossible to train your agent on all the possible states. So can your agent work in new environments, such as if you train your car in sunny environment, can it work in rainy states? And finally, offline IL, can we learn from fixed data sets? So after we collect data sets, we may have we may wish to train our agent on this data set only because it is expensive to collect more data, and it's also expensive to train your agent online because basically interaction is expensive. And so these are the four of the challenges that are still active research problems, and there are more that I'm not able to list here.
Maybe one question
Yes.
also is that um, with with this challenge, I guess what would be the trend of its um, being what would be the like the most potential near-term breakthroughs that will make RL a lot more useful in what way? And then with also with this problems, what like how not effective it had made the RL to be. I guess it's asking this is just to give to ask you for your expert opinion for all the practitioners, ML practitioners here to see how uh how do they where do they should say like is RL the next big thing or how far are we from it?
Yeah, I think IL is still developing. So LLM, like the NLP era, this I think is quite developed already. However, IL I think is still developing, and currently I think there are two main trends. The first trend is the world model stuff. Basically, you try to learn a model of the world, let's say the transition function, or maybe the some other aspects of the world. And the second trend is the zero shot IL. So zero shot IL is what enables your agent to generalize. So the key idea is that we actually represent the environment using some form of a vector, basically. And then you try to basically learn a vector for a bunch of environment, and then basically this vector computes. So the formula basically says that the vector of a given environment should consist of some a first embedding network. So we embed the state into a vector, and then we multiply embedding by a reward function. So we use this formula to sort of compute a representation of the environment, and then we hope this form of a representation can generalize to new environments. So in this case, we assume that given a new environment, we can take a bunch of steps, and then we can observe the states, and we can observe the reward. And then based on the observed states and reward, we can sort of compute a vector to represent this environment. And so I think this is the other direction that are currently developing. Yeah.
Mhm. Thank you, thank you, thank you. Basically, it's still in the it's promising and it's very useful in
Yeah.
small directions.
Mm.
And particularly that helping different AI system to make better decisions.
Yeah.
But itself haven't been a major uh direction yet.
Mm.
It used to have some breakthroughs, I think, in like playing video games or
Yeah. Yeah.
like but it haven't been like having a very significant real world applications. And
Yeah.
then it's just a but it's a very important architecture where many experts say it could potentially be next big thing, could be one of the most important architecture that help uh, LLMs to solve the decision making problem later,
Yeah.
but still have many unsolved problems.
Mhm.
There you go.
So the key takeaways of this discussion is that RL basically we learn from interaction, and the goal is to maximize long-term reward. And we have a bunch of tools in our bag, such as policy function, value functions, and MDP framework. And so we now have the language to understand modern reinforcement learning. So next week we are going to learn something interesting, which is called the Q values or the quality values. So we'll go from intuition to algorithms such as Q learning and also deep Q learning. So looking into the future, so if you want to go beyond intuition and build your own IL agents, you can go to this GitHub repo, which is CleanIL. And this is a collection of simple single file implementation of IL algorithms. And this is great for learning and experimentation. And you can try running code for myself, and that will be your first IL agent. So let me open this. So this is the repository. Well, these are the algorithm that it implemented. We'll discuss most of them in the next few weeks. So basically, it's very simple. So single file implementation, which makes your life very easy. And it has implemented 7 algorithms plus many games. And we have all sorts of logging metrics, which is quite cool. And let's open a single file. So let's open dqn.py. So basically, so first we have these configurations, which we can ignore for now. Let's look at the main part of it. So the first part is, which we'll discuss, the Q network that basically takes in the state and outputs the values of the actions. So in this case, it's Atari, so we assume the actions are discrete. So maybe there are 16 actions or less than that. So the training basically, so basically so this is the training part. So we sample some data from the what we call the replay buffer. And basically, we'll talk about these formulas. So the key idea is that we have a buffer that contains our experiences, and then we train our network on these experiences such that our network can correctly estimate the Q values, basically. And so typically the code will consist of two steps. The first step is just basically we collect a bunch of data, typically just using random exploration. And after we collect enough data, we start the training. And then after we train, we collect more data, and then we train again, and then until we are satisfied, typically maybe 1,000 or 10,000 episodes. Any questions?
My understanding is that we will be able to go into this more in depth next class.
Yes, yes.
And then also for people who want to actually, would this be a piece of code you recommend people to run before the next class?
Yes, try run it. And then there are especially,
Specifically deep Q learning.
yeah, deep coding. So
Deep
if
Q
you,
learning, that's a very good file.
yes,
Actually, if you can send that URL to the group chat, that would be good too. The specific the deep Q learning URL. If you can just yeah. And then I'm also thinking is that uh are you going to be running this yourself next class, or you actually be looking for some students who are interested in running it to actually run?
I think I'm looking for a student to demo it, I would say.
Yeah, yeah, okay. So for um if you are actually any of you are interested in demoing, uh in demoing, uh can you please reply under this message? Uh
Yeah,
on the
so you can play with this code, and then to run it is actually very simple. You just run this command, and then you'll see something.
uh so if you can do that, so yeah, reply your message with your contact, prefer email, but if you
Mhm.
also have use the other ones, that's okay too. And then we will at the end of the next class or the middle of the next class, we will have you to be able to share your screen and actually
Mhm.
show running the deep Q learning on there. Yes.
Yeah, email address.
Email address is good, yes. Next class will literally be same time next week,
Yes.
Saturday, the same time. And so just here. And then also it's and this will be running in the OpenAI's uh what you call the OpenAI's environment. Because when I was watching that
Yeah.
video, it's called the
OpenAI Gym. Yeah.
OpenAI Gym. Yes, yes,
Yeah.
yes. It was uh
Yeah.
would you like to
So,
tell us a tiny bit about OpenAI Gym?
yeah. Right now it's called Gymnasium actually, and for this code because it's not a new, so they use the older version of Gym. Let's open the documentation actually. So this is oops.
But right, that's that's
Okay. Yeah, so this is the new gymnasium. So gym is the older version. And for here, you will find all kinds of environment. For example, the carport that I talk about. And you will find we have discovered the action space, your observation space. And at the bottom, you will find how to run it actually. So you can use this code to inspect the environment. And there are other environments. So you may know the Atari. Oops. Atari is the very classic environment to train the IR agent, and these are all sorts of arcade games you may play yourself as well. And yeah, and then you can find how you install your specific platform. I just run it on my school server. So yeah, and then you can try it on your Mac or Windows as well. Cool.
Okay. Um, Amazing, amazing. And then, can you share this link as well?
Yeah, sure.
Yes. Uh, in the chat. Okay. All right. Is that about everything, Kobe?
Yeah, that's about it.
Slide. Okay, cool. Then one thing that we want to do is that